Good morning, students.
Good morning.
Good morning, sir.
Good morning, all of you. So, last class we have seen the discussions of heating of carboxylic acids in that 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7 acids we have heated and seen what type of compounds obtained. So, whenever you heat 1, 2, 1, 3 acids, you undergo loss of CO2, you get acids. Whenever you heat 1, 4, 1, 5, you will undergo loss of H2O, you get an anhydride, cyclic anhydride based on Planck's rule. Whenever you hit 1, 6, 1, 7 acids, you will be getting a loss of CO2 and H2O and a cyclic ketones are obtained, 6-membered and 5-membered rings. Right? After this, if you look at some of the derivatives, after the reactions, preparations, properties of carboxylic acids, let us look at some of its derivatives. The characteristic reaction of carboxylic acid derivative is nucleophilic substitution, and the nucleophilic substitution is going to happen by addition elimination type. Nucleophilic substitution is actually happening by addition elimination. Why? Because the nucleophile RC double bond O Z, it will be giving what? RC double bond O Z attacked by a nucleophile. Nucleophile is going to attack the electrophilic carbon. Pi electron density moves away. You get RCO minus CNUCZ. Z is a leaving group. Negative charge on oxygen comes into loss of Z minus occurs. You get RC double bond NU. This is addition. This is elimination. Ultimately, substitution occurred by addition elimination. The nucleophilic substitution reaction happened with respect to carboxylic acid derivative, but by addition elimination type. Mechanism: nucleophilic substitution by addition elimination. So RC double bond Z, nucleophile attacking the electrophilic carbon, that is your rate determining step. So based on that RDS only you have to compare which is going to be the major product and which will be the minor product. You get RCO minus CNUCZ, which is the addition product. Negative charge on oxygen comes into loss of Z minus occurs. You get the elimination product. This reaction is also called as acyl substitution. Why it is said to be acyl substitution? Since the acyl group, C double bond O group, has been substituted, the substitution occurred at the C double bond O. That is why it is also called as acyl substitution reaction. Very simple. The same discussion we have done. RC double bond O group is said to be acyl group. On the acyl group, substitution has been done. So that is why the name acyl substitution. Rate towards nucleophilic substitution is directly proportional to electrophilicity of carbonyl group. Like I have told you many times earlier also. What is the order? Like if you compare acid halides, acid anhydrides, esters and amides, which are more reactive towards nucleophilic substitution?
Acid halides and
Acid halides, then anhydrides, then
Anhydrides,
esters,
esters,
esters.
then amides. Right?
amide.
Like you can take, you can simply understand this point by minus I effect of halogen is dominant here. Anhydride, lone pair of oxygen is in resonance with the two groups, with the two C double bond O, thereby the charge, decrease in charge is less, obviously more electrophilic. Here, lone pair of oxygen in resonance, and here we have lone pair of less electronegative nitrogen in resonance. The effective resonance is going to be seen in amides, thereby it will be having the least electrophilic character for the carbon of C double bond O, thereby it is least reactive towards nucleophilic substitution reaction by addition elimination. Acid halide is most reactive towards nucleophilic substitution in acid derivatives, and amide is least reactive. For acid halide and anhydride, generally we don't need to increase the electrophilicity. For acid halide and anhydride, we generally don't need to increase electrophilicity of carbon as they are more electrophilic. Even though in the case of pure nucleophile, we are not using any acid to increase the electrophilicity because they are already more electrophilic in nature. Try to look at this example. Which of the following esters gets hydrolyzed most easily under alkaline conditions? Under alkaline conditions, like which esters are going to be hydrolyzed more easily?
ABC.
A, B, C.
Why?
Electron withdrawing
electron
group.
withdrawing.
NO2 is a very good electron withdrawing group, minus M effect. Chlorine is minus I effect.
Minus I.
Here we have no effect. Yes or no? Here what should happen is the nucleophile has to go and attack this particular electrophilic carbon. The pi electron density moves away. You will be having this scenario. NO2, O, CO minus, C nucleophile. Hydrolysis in the presence of alkaline condition. Alkaline condition means OH minus will be acting as nucleophile. So we can write simply OH minus here instead of nucleophile. Yes or no? Alkaline condition, students. So base OH minus, I am trying to attack this electrophilic carbon. First I am doing the addition. Then I have to do the elimination. If I am doing the elimination, negative charge and oxygen comes into CO minus bond is going to be cleaved. I am generating this particular phenoxide ion with a substituted ion, with a substitution at para position. Yes or no? This is the phenoxide ion. The phenoxide ion is resonance stabilized because of electron withdrawing groups. What happens? The charge on this particular ring has been decreased. Because of decrease in charge, the stability has been increased. So NO2, which is electron withdrawing group, stabilizes the phenoxide greatly, thereby having more reactivity towards hydrolysis in the alkaline condition. So A greater than B greater than C, that's the right order. Like if you think of just because of electron withdrawing group, how the rate is affected. I'm just comparing the stability of phenoxide because that phenoxide is lost, like a substituted phenoxide, and comparing the respective rates. Acetyl chloride, if you take CH3 C double bond to Cl treated with NaOH, Na plus OH minus, what will happen, students? The OH is going to replace acetic acid will get, and again the reaction is by addition elimination type. Addition elimination type. C2H5O Na, C2H5O minus Na plus. You have C2H5O minus that is going to attack the electrophilic carbon. C double bond O, pi electron density moves away. C2H5O minus, alkoxides can act as nucleophiles as well as bases, but here they are going to act as nucleophiles because we have electrophilic carbon, more electrophilic carbon. CH3 C double bond O minus Na plus will get what here? Acetyl chloride. Acetate ion is going to act as an respective nucleophile, attacks the electrophilic carbon. You generate the anhydride. Yes or no? Like if you go with this reaction, CH3 C double bond O CCl plus CH3 C double bond O minus. This O minus will be attacking this particular carbon, C double bond electron density moves away. CH3 C O minus CCl O C double bond O CH3 you will get. Negative charge and oxygen comes into, chloride leaves. You generate CH3 C double bond O C double bond O CH3. The chloride lost will develop electrostatic attraction with Na plus. So this is how the mechanistic approach will be there. Similarly, H2O. In the H2O also, do we require acidification? As I have told you, H2O, even though it is a pure nucleophile, since the acid halide is more electrophilic in nature, even though the pure nucleophile H2O can attack. Even though H2O is a pure nucleophile, it can attack because acetyl chloride or acid halides are more reactive towards nucleophilic substitution. So same you have acetic acid formed. These are the set of reactions where acetyl chloride will be undergoing set of nucleophilic substitution by addition elimination type. We can also have acetic anhydride similar to acetyl chloride. Acetic anhydride treated with ROH, you get CH3 C double bond OR, PHOH, RNH2, PHNH2. What is going to happen now? Like let us do the reaction with NH2. Acetic anhydride, CH3 C double bond O C double bond CH3. I am treating with RNH2, RNH2. Acetic anhydride is also more reactive towards nucleophilic substitution by addition elimination. Why? Because the carbon is more electrophilic. Lone pair of electrons and nitrogen, they attack the carbon. C double bond of pi electron density moves away. You will generate what? CH3, C double bond O, O, C, O minus, C, CH3. Carbon connected to nitrogen. Nitrogen will have positive charge, 2 NH bonds, and an alkyl group. Yes or no? And now what happens? Negative charge and oxygen comes into this acetate ion is going to be lost. You will generate CH3, C double bond O minus. Along with that, you have CH3, C double bond O, nitrogen positive charge, 2 NH bonds, and 1 alkyl group R. The acetate ion can pick up this proton. Why? Because NH electron density is moving towards nitrogen. Ultimately, it will lead to the formation of what? CH3, C double bond OH plus CH3, C double bond O, NH R, where lone pair of electrons and nitrogen present. So this is your product. The same product we get. CH3, C double bond O, NHR. If you take pH NH2, instead of R group, you have pH group. So acetylation and benzoylation of ROH, PHOH, RNH2, PHNH2. Like ROH, we are converting into what? The hydrogen has been replaced with CH3, C double bond O. PHOH is replaced with hydrogen replaced with the CH3, C double bond O. So acetylation and benzoylation of ROH, PHOH, RNH2, PHNH2, that is said to be Scottman-Bowman reaction, and acetylation means hydrogen is replaced with acetyl group, CH3, C double bond O. And the mechanism is simple. Is that clear, students?
Yes.
Yes, sir.
Yes or no? And why do we require a base here? Base they have mentioned, no? So try to answer, why do we require a base?
So that acetic acid formed can be reduced to acetate ion and reaction can proceed in forward direction.
Very good. But the base should be stronger base or weaker base than the respective amine, RNH2. Like we have RNH2, no? Amine. Amine is also base. The base, whatever you are considering here, that should be a stronger base, so that can remove all the
Weaker
acetic
base.
acid. Weaker base or stronger base?
Sir, weaker.
Why?
That base will react with anhydride, right? If we take stronger.
If we take a stronger base, that will react with, like if you look at
Anhydride.
the acetylation, like if you look at the acetylation of amines, look at the acetylation reaction of amines, what type of base you are going to choose is like pyridine. Pyridine and amine, you compare which is more basic. Compare.
Sir, amine.
Amine should be more basic because sp2 hybridized carbon, right? Like nitrogen is sp2 hybridized in the pyridine, whereas amine in that sp3 hybridized. So less electronegative nitrogen that can be easily donating its lone pair. So electron density can be easily donated. So amines are going to be strong bases. So we have to take a base so that the base will try to pick up the respective acetic acid, and a preferable base is pyridine. The same we are going to do even in the acetylation reaction, because if we don't take the base is not actually picking the proton here. People generally gets confused. The NH bond, whatever is there, right, that proton has to be picked up, that can be done by a base. No, the base is actually removing the acid formed in the reaction, so that the reaction is going to be moving in the forward direction, and preferable base is pyridine. Salicylic acid, if you treat with CH3, C double bond O Cl, CH3, C double bond O, OC double bond O CH3, which groups are going to be affected? Here, do we need to think of esterification reaction or different other
Yes,
reaction?
esterification.
No, not esterification. Why?
Because OH group will be affected in this reaction.
Yeah, OH group is going to be affected from the salicylic acid, like COOH affected with the alcohol, like acid carboxylic acid and alcohol in the presence of acid medium means then esterification. Here OH group is affected. Lone pair of electrons and oxygen, they are going to be like OH, hydrogen has to be replaced with C double bond of CH3. We have this reaction, COOH, lone pair of electrons present on oxygen plus positive charge, oxygen, CO minus, CCH3, CCl. Same mechanism, lone pair of electrons attacking the carbon, C double bond of pi electron and moves away. Negative charge comes into chloride loss of chloride ion occurred. COOH, oxygen with one lone pair positive charge, one OH bond, C double bond of CH3, and the last chloride ion that is going to pick up this proton. As soon as picks up the proton, you will get what? You will get COOH, oxygen regain its lone pair, C double bond of CH3. So it is not your respective esterification reaction, it is the acylation happening. So which will lead to the formation of aspirin. Aspirin is an analgesic. Yes or no? Aspirin is an analgesic or not?
Yes, sir.
Aspirin is an analgesic which is going to be a narcotic or non-narcotic.
Narcotic, sir.
Narcotic means addictive or non-addictive?
Addictive.
Addictive.
Aspirin, is it addictive?
Sir, my father.
No.
Okay,
Sir, yes,
addictive
sir.
are three: morphine, heroin, codeine. Okay, it is not addictive aspirin. Aspirin, paracetamol are not addictive in nature. So there are two types of analgesics. Analgesics are those species which are going to reduce the pain. Those substances or those medicines which are going to reduce the pain without causing any impairment to the nervous system. The nervous system is not going to be affected, only the pain has to be controlled. In that case, we have two types of analgesics, like narcotic and non-narcotic, like addictive, non-addictive. So in the addictive part, you have heroin, codeine and morphine, where in the heroin, codeine and morphine, you are going to have, like, they are the drugs which can be addictive in nature and which can cause severe damages to the nervous system also if taken in extra doses, and they are only useful after the post-operative pain. But aspirin, paracetamol, they are going to be useful for normal headaches and all. Yes or no? And they are going to bind to the respective receptors. Yes or no? How the pain is going to be reduced? Because of some enzyme, like enzyme is going to be there where the substrate is going to go and bind to that particular enzyme. Because of that, some product is going to be obtained. Like pain is generally caused by inflammation of the tissues. The inflammation of tissues is going to be reduced because this aspirin drug will be acting as a competitive inhibitor or allosteric site. We'll discuss all the details in the chemistry in everyday life, like how a particular drug can actually control the or reduce the production of more product. Like if you are having more extra acidity, or if you are allergic, or if you are having pain. So under different categories, we have different types of drugs. How this drug is going to be effective and what were the reasons and what was the mechanistic approaches. We'll discuss the details. Reactions of acid derivatives with Grignard reagents, like CH3, C double bond OCH3, CH3 MgBr excess we have taken. So first CH3 minus MgBr plus, CH3 minus is going to attack the electrophilic carbon, C double bond of pi electron and moves away. You get CH3 CO minus, CCH3 OCH3, negative charge and oxygen comes into carbon oxygen bond cleaves. You generate what? CH3 C double bond of CH3 plus CH3 O minus. Yes or no? Again, this is going to be attacked with next mole, CH3 minus MgBr plus. Negative charge attacks this particular carbon, C double bond electron and moves away. You generate CH3 C O minus, CCH3 CCH3. This upon hydrolysis will form CH3 COH, CH3 CH3. A tertiary alcohol is going to be formed and 2 moles of Grignard agent has been reacted. Ultimately, what you will get? How many moles of Grignard agent reacted? 2 moles, because the first mole convert the respective ester to respective carbonyl, that is ketone, and the second mole converted the respective ketone to respective tertiary alcohol. reaction of acid derivative with Grignard agent, and this was the first example in that category. So this will be about the discussion of aldehydes, ketones, carboxylic acids, and derivatives, different points. So let us start with the next chapter named amines, like nitrogen containing compounds and its derivatives. Nitrogen containing compound, students. Amines can be considered as derivatives of ammonia. Like we have ammonia, right? NH3 is ammonia. From the ammonia, all of you can see the slide, right?
Yes. Yes.
Yes. So amines can be considered as derivatives of ammonia obtained by replacement of 1, 2, or all the 3 hydrogen atoms by alkyl or aryl groups. You can also replace the lone pair of electrons and nitrogen with alkyl group, and you can generate quaternary ammonium salts also. So classification of amines. Amines are classified according to number of carbon atoms bonded directly to nitrogen atom. So if you have only one group connected to nitrogen, so we have NH2 group connected to alkyl group. In that case, we call them as primary amines. If you have NH group connected to two alkyl groups, the two alkyl groups can be same or different. In that case, they are called as secondary. Nitrogen connected to three alkyl groups, all the three can be same or all the three can be different, the tertiary. And quaternary means, like this is a primary again, because NH2 is connected to only one alkyl group, that is a primary again. So quaternary ammonium salts means you have nitrogen, used its lone pair, you get alkyl group R1, R dash, R double dash, R triple dash, R4 dash. It will be having some electrostatic force of attractions with some anion. This is nothing but quaternary ammonium salts. Quaternary ammonium salts. Amines are classified based on the number of carbon atoms connected to that particular group. So we have primary amines, secondary amine, tertiary amine, and also quaternary ammonium salts. First, you have to look at the respective methods of preparations of amines. The methods of preparation by the reduction you can do by reduction of nitro compounds, by reduction of nitriles, isonitriles. You can also do the reduction of amides. You can also do the reduction of oximes. Reduction reactions, with the reduction you can produce respective amines. After that, you have to do the ammonolysis. After ammonolysis, you can think of Hoffman's bromide degradation, Gabriel Thallimide synthesis. All these are the methods of preparations of your respective amines. Let us start with one by one. First one, reduction of nitro compounds. Reduction of nitro compounds will happen under what reducing agents? If I have a nitro compound like RNO2 or PHNO2, I can treat that with H2 in the presence of palladium, metal catalyst, or I can treat with a tin in the presence of HCl, or iron in the presence of HCl, or zinc in the presence of HCl. You are going to have nitro compounds are reduced to amines by passing hydrogen gas in the presence of finely divided nickel, palladium, or platinum, and also by reduction with metals in acid medium. Reduction with the metals in the acid medium, or H2 in the presence of palladium or lichen or platinum. What is going to happen in the total course, students? Like I have taken nitrobenzene, NO2, and how many hydrogens are going to be added? 6 hydrogen atoms we are going to add, and those are obtained by metal like T in the presence of HCl, or ZnHCl, or FeHCl, and you will be generating what? The hydrogens are added to nitrogen as well as oxygen. For each oxygen, you will be adding 2 hydrogens, so that you will be getting H2O, and you have NH2 here. and here you will be having 2 H2O. So ultimately 6 hydrogens you are going to add. Nitro compounds are reduced to respective amines by passing through finely divided nickel, palladium, platinum by passing hydrogen gas through these metals so that adsorption can happen, or also metal in the presence of catalyst, metal in the presence of acid. We can use these reducing agents. Similar to nitro compounds, we can also do the reduction of nitriles and isonitriles. If I take nitriles, RC triple bond N, this has to be converted to RCH2NH2. So how many hydrogens I'm adding? RCH2NH2, this carbon 2 hydrogens, this nitrogen 2 hydrogens. So 4 hydrogens I have added. And what type of reducing agents I can take? Reducing agents. So here you can take Ra. Ra stands for reducing agent. Reducing agent you can use lithium aluminum hydride, H2 in the presence of palladium. Reducing agents you can do LiAlH4 or H2 in the presence of palladium. Palladium or metal catalyst, any metal catalyst. You can also add sodium in the presence of ethanol. If you try to reduce the respective nitriles with the sodium in the presence of ethanol, that is specially named as Mendius reaction. Okay, reduction of nitriles and isonitriles. Nitriles on reduction with lithium aluminum hydride or catalytic hydrogenation produce primary amines, but isonitriles produce secondary amines because isonitriles will have this structure R N triple bond C. If I am trying to add hydrogens, I will be adding 1 hydrogen to the nitrogen and 3 hydrogen to the carbon. So you get RNH CH3. Again 4 hydrogens were added in total. Again same reducing agents. The same reducing agents you can use. Primary amines are going to be formed when you try to reduce the nitriles. Secondary amines are going to be formed whenever you try to reduce the isonitriles, because in isonitriles we have alkyl group connected to nitrogen and nitrogen triple bond carbon. So nitrogen triple bond carbon is going to be converted to NHCH3. So it is not going to be a primary amine, rather we get a secondary amine. Is that clear, students? Reduction of nitro compounds, reduction of nitriles and isonitriles.
Yes, sir.
Yes, sir.
Yes, right.
Yes.
And don't go with the mechanistic approach. You may ask a simple question, sir, how we are simply adding the hydrogen atoms. It's not some number to add. Yes or no? The hydrogens are going to be added to the pi electron densities, not like addition of 2 numbers. So there are a lot of mechanistic approaches where adsorption is going to happen in the presence of H2, in the presence of nickel. In the LiLH4, hydrogen ion is going to be obtained. Then the C- will pick up the proton. So like that, different mechanism with different type of reducing agents. Those are not required for you. You have to know what type of compound is going to be obtained and what are the reducing agents. Nitriles, you will get primary amine, isonitriles secondary amine. Mendius reaction means what?
Sodium in the presence of ethanol.
Same reaction, RC triple bond N, sodium in the presence of ethanol. You will generate respective RCH2NH2. Same reduction of nitriles in the presence of sodium and ethanol. That is said to be your Mendius reaction. Reduction of amides. Amides means RC double bond NH2. You have to reduce this. And how many oxygens you have to supply? How many hydrogens you have to supply, provide? You have to remove the oxygen. Oxygen is removed in the form of H2O.
2
You have to
hydrogens.
convert the carbon also. CH2, RCH2NH2 plus H2O, so 4 hydrogens. 4 hydrogens. Reducing agents. Ra. Reducing agents, what you can use? LiLH4 in the presence of H2O, H2 in the presence of metal catalyst, sodium in the presence of ethanol. All the three same. LiAlH4 in water, explosive reactions. H2 in the presence of metal catalyst like palladium. Sodium in ethanol. So you can use all these three. You can reduce the respective amides to respective What type of compounds you are getting? Primary amines. So primary amines are obtained whenever you try to reduce the respective amides in the presence of reducing agents like lithium aluminum hydride or H2 in the presence of palladium or sodium in the presence of ethanol. We can also have next reduction, that is reduction of oximes. Next one is reduction of oximes. What are oximes? Where you have studied about oximes? If you remember, we produce RCH double bond NOH. Like aldehyde, if I take and react with a NH2H, you will get a like RC double bond OH treated with NH2H hydroxylamine. You get RC double bond N RCH double bond NOH. Acetyl oxime you will get whenever you take the aldehyde. If you take the ketone, you get a ketoxime. So oximes are C double bond RCH double bond NOH treated with reducing agents. What type of reducing agents? LiAlH4 lithium aluminum hydride, H2 in the presence of palladium, sodium in the presence of ethanol, H2 in the presence of palladium, sodium in ethanol. Here or you will get what? Or CH double bond NOH. What you are going to get, students?
RCH2 NH2.
Or CH2 NH2 is going to be obtained. So respective primary amines are going to be obtained. The primary amines are going to be obtained whenever you try to reduce the reduction of amides. Whenever you try to do, you will be getting primary amines back, right? So these are the different reduction reactions, students. So if you perform the reduction of nitro compounds or nitriles or isonitriles or amides or oximes, you will be generating respective primary amines or secondary amines. That depends upon the type of substrate whatever you have chosen. Next type is ammonolysis of alkyl halide. Alkyl halide ammonolysis, if you try to look at the ammonolysis of alkyl halide, what is going to happen is alkyl halide on reaction with the ethanolic solution of ammonia undergoes a nucleophilic substitution in which a halogen atom is replaced by amino group. The process of cleavage of CX bond by ammonia is known as ammonolysis. So nucleophilic substitution occurs and you will be getting primary amine. Ammonia react with alkyl halide, you get a primary amine. The primary amine react with alkyl halide, again you get a secondary amine. The secondary amine react with alkyl halide, you get a tertiary amine. Tertiary reacts with alkyl halide, you get a quaternary amine. When you are going to have more primary amine only, if I am getting mixture, primary, secondary, tertiary, quaternary, I am getting mixture. When I take ammonia in excess, what I will be getting?
Primary amine.
Primary amine in major, because ammonia molecules are excess. The whatever the alkyl halide is obtained, the alkyl halides, all of them will react with ammonia only instead of primary amines. So you will get primary amine as a major. When I take alkyl halide in major, which will be when I take alkyl halide in excess, which will be major?
Quaternary salt.
Quaternary ammonium salt. Okay, very good. If I take ammonia in excess, all the alkyl halide will try to react with different ammonia to form primary amine. If I take a alkyl halide in excess, then all the alkyl halide molecules are going to be reacting further and further, leading to the formation of quaternary ammonium salts. Mechanistic approach is simple. Ammonia reacts with alkyl halide. So Rx bond is polar, partial negative one halogen, partial positive one carbon, lone pair of electrons and nitrogen attack the alkyl group. You'll generate what? Loss of halide ion occurred. Because of loss of halide ion, you'll get a nitrogen already has 3 NH bonds, and the lone pair of nitrogen is used to the new bond. So nitrogen will have a positive charge. So halide ion, which is present in the reaction mixture, that will try to pick up the proton. NH electron is given to nitrogen, generating RNH2. This will react with the next molecule. This will react with one more molecule of alkyl halide, lone pair of electrons and nitrogen. You will generate R, NH, R, same mechanism. This will react with one more molecule of alkyl halide. It will form R, NR, NR. It will react with one more molecule to form R, N, R, R, R. This total will have positive charge, electrostatic force of attraction with minus. This was the mechanistic approach. First mechanism, first step for the preparation of primary amine, we have seen the same repetitive steps. Lone pair of electrons again attack alkyl group, halide lost, halide picks up the proton, generates RNHR. Again same lone pair of electrons and nitrogen attack the electrophilic carbon, halide leaves, generate tertiary amine. Again same reaction, you get a quaternary ammonium salt. Ammonolysis reaction yields a mixture of primary, secondary, tertiary amines and also quaternary ammonium salt. However, primary amine can be obtained as a major product taking large excess of ammonia. As I have told you, if you take excess of ammonia, you get primary amine as a major, and quaternary ammonium salt will be major if alkyl halide is taken in excess. If alkyl halide is taken in excess, you will get a quaternary ammonium salt will be the respective major product. Is everything clear, students, so far?
Yes, sir.
Yes.
Yes, sir.
Yes, right. Gabriel Thalamide synthesis. Yesterday we have prepared Thalamide. How? How we have prepared
Amides
Thalamide?
reaction.
Yeah, we have taken phthalic acid. C double bond OH. C double bond OH. Phthalic acid we have treated with ammonia. What happens? Ammonium phthalate you will get. Like a salt is going to be formed. If you heat it, you will undergo loss of water. 2H2 is going to be lost. You get amides. C double bond O NH2. C double bond O NH2. If you heat it strongly, what is going to happen?
Ammonia is removed.
Ammonia is removed, and we have seen the mechanism yesterday. Simply ammonia is going to be removed. Loss of ammonia, you will get from phthalamide to thalamide, you will get C double bond O NH, C double bond O NH. This is nothing but your thalamide. Okay, Gabriel Thalamide synthesis. So we have directly taken thalamide. This is just the method of preparation of thalamide from the phthalic acid. Gabriel Thalamide synthesis, that is a preparation of primary aliphatic amines only. Thalamide on treatment with ethanolic potassium hydroxide forms potassium salts of thalamide, which on treatment with alkyl halide followed by alkaline or acidic hydrolysis producing the corresponding primary amines. So this was the reaction, but we have to understand the mechanistic approach. The thalamide you have taken, treated with alcoholic OH, then treated with alkyl halide, then done the acidic or basic hydrolysis. We have done the acidic basic hydrolysis here. We obtain the primary aliphatic amines only. Only primary aliphatic amines can be prepared, not the aromatic amines, not secondary amines, not tertiary amines. Only primary aliphatic amines can be prepared using this method. Mechanistic approach we will look at. Thalamide you will take C double bond O NH, C double bond O. First alcoholic OH will do what? Alcoholic OH. Alcoholic OH, whenever you see, you will be thinking of elimination reaction in the, you will be thinking of elimination reactions if you go with the respective alkyl halides. But here there is no possibility of elimination, whereas OH minus has to pick up the proton only, base only. So ultimately from the reaction mechanism, whatever they have given, you can understand this easily, right? OH minus picks up the proton, NH electron density is given to nitrogen. Nitrogen gets negative charge, and negatively charged nitrogen develop electrostatic attraction with K+. So potassium salt of thalamide. This step is simple acid-base reaction. Now it is going to be reacting with alkyl halide. Can I say negatively charged nitrogen acts as a nucleophile, attacks the electrophilic carbon, loss of halide ion. the halide ion and K plus will develop electrostatic force of attractions. So Kx is going to be formed. You get what? Nitrogen and alkyl group, Nr new bond is going to be formed. So C double bond O, C double bond O, Nr, N-alkyl phthalimide is formed. So let us start with N-alkyl phthalimide directly. These two steps are very simple. That N-alkyl phthalimide, if you try to do the hydrolysis in the basic medium, you will get respective carboxylates. How is that obtained? That is very important to you. So we are treating this with OH minus. OH minus will be acting as a nucleophile. That nucleophile is going to attack the electrophilic carbon, C double bond electron and moves away. You get this intermediate. CO minus. C double bond O, Nr. Carbon is also connected with a OH. Now can I say negative charge on oxygen when compared to negatively charged oxygen like CO minus, the C double bond O is more stronger. So negative charge on oxygen comes into the carbon nitrogen electron density will be moving towards nitrogen. Because of that, what is going to happen? You will generate a 6-membered ring as it is. C double bond O, OH. You have C double bond O. Nitrogen will have negative charge or not now?
Yes, sir.
Neutral atom getting an electron density, it will get negative charge. So negatively charged nitrogen will be picking up this proton. As soon as this picks up the proton, you get this formed, this product. C double bond O minus, because C double bond OH is acidic group. So from that, the H plus has been picked up. So we will generate C double bond O NHR. Again, the next mole OH minus attacks this particular carbon, electrophilic carbon. C double bond O pi electron density moves away. You get what? C double bond O minus, CO minus, COH new bond connected with NHR. Ultimately, this what happens, students? This O minus comes into this carbon nitrogen electron density is given to nitrogen, generating C double bond O minus, C double bond OH plus NH negative charge nitrogen and R. So negatively charged nitrogen will pick up this proton. These set of compounds will lead to C6 H4 C double bond O minus, C double bond O minus plus R and H2 primary amine. Yes or no?
Yes, sir.
So look at this reaction carefully. In this particular reaction, negatively charged nitrogen picks up the negatively charged nitrogen attacks the electrophilic carbon and carbon halogen bond leaves. If I take a X group connected to some phenyl ring, is that possible?
No, sir.
Okay. Aromatic amines, aromatic primary amines can't be prepared. Aromatic primary amines can be prepared as carbon halogen bond exhibits partial double bond character. Partial double bond character. Only aliphatic primary amines can be prepared. You can do the acidic hydrolysis or basic hydrolysis. Here we have done the basic hydrolysis. If I do the acidic hydrolysis, what happens? How the reaction is going to be happening? If I do the acidic hydrolysis, since H2O cannot directly act as a nucleophile and attack, first what happens is lone pair of electrons on oxygen, they will pick up the proton, thereby increasing the electrophilicity, thereby the nucleophilic attack. In the case of acidic hydrolysis, H2O acts as a nucleophile. So H2O is a weak nucleophile, so lone pair of electrons on oxygen, they will pick up the proton first, then the H2O will be acting as a nucleophile and attacks the electrophilic carbon. Got it, students?
Yes, sir. Yes, sir.
Yes, right. Next, like after Gabriel phthalimide synthesis, we have to understand about Hoffman's bromamide degradation reaction. In the Hoffman bromide degradation, what is going to happen? First, understand the concept, like what is the reaction, what are the substrates and products, and what are the important notes. RC double bond NH2 amides. Amides you are taking treating with Br2 in the presence of NaOH. You are getting amines Na2CO3, H2, and ABr. Primary amide has been converted to primary amine because it is not any substitute amide. Primary amide converted to primary amine. X2, how many mole you have to take? 1 mole. Base you have to take 4 mole. RC double bond NH2 converted to RNH2. That means one carbon has been less in the amine when compared to amide. In the amide, the carbon, whatever it is there, that is lost in the form of CO3 2 minus, not a CO2. The carbon is lost in the form of CO3 2 minus, not in the form of CO2. Everyone got this or not?
Yes, sir.
Yes, right. So how is the reaction is going to happen now? So that is again a point to understand. Hoffman's bromide degradation. First reaction is going to be like R C double bond NH2 is now going to be reacting with respect to Br2 in the presence of NaOH. 4 moles of base and 1 mole of Br2 is used. The first step is simple. We have taken amide. R C double bond NH2 we have taken. Lone pair of electrons and nitrogen are there and 2 NH bonds are there. We have a strong base NaOH. The strong base NaOH can pick up this proton or not? OH minus that can easily pick up this proton, leading to the formation of R C double bond O NH. As soon as this proton is picked up, the NH electron density is given to nitrogen, developing negative charge on nitrogen. The negatively charged nitrogen can be reacting with Br2. Bromine you have taken. The negatively charged nitrogen can pick up the, like bromine is non-polar, but polarity can be induced because one of the bromine atom at any point of time can be closer towards this negatively charged nitrogen. So that from that bromine electron density moves away. So you form a new bond and loss of bromide occurs. You will generate RC double bond O NHBr and loss of bromide is going to be happening. Now again we have NH bond. Again we have a base RC double bond O NHBr. Again we have NH bond. This up to here 1 mole of base has been used, 1 mole of Br2. The next OH minus second mole, OH minus again picking up the proton. OH minus again picking up this proton. NH electron density is given to nitrogen, developing RC double bond O N minus NBr and H2O is obtained. OH minus picked up the proton. Since OH minus picked up the proton, H2O is obtained. Now what happens is intramolecular alkyl shift occurs. What happens in this now case is, now it is not N minus attacking the Br2. Br2 1 mole already used up. Now the rearrangement happens, students. The alkyl shift is going to happen, intramolecular alkyl shift. Like as soon as the alkyl shift occurs, what happens? The bromine is going to be lost and negative charge on nitrogen comes into. So we'll generate R. Alkyl group is now connected with nitrogen. Nitrogen doubly bonded with carbon. Carbon doubly bonded with oxygen and loss of bromide ion. Everyone got this or not? Alkyl isocyanate is going to be formed. This is formed with the second molecule of OH minus. This is formed with the second molecule of OH minus. Alkyl isocyanate. So let us continue here. R C double bond O. Let us go with the previous discussion only because you can have OH minus, right? OH minus again there. So we can complete the total mechanism. OH minus, like this is alkyl isocyanate form. That alkyl isocyanate is going to be attacking this particular carbon. As soon as that attack that particular carbon, what you are going to have? The C double bond of pi electron density moves away or not? So if you get confused here, we'll write the step like this. R N double bond C double bond O. This alkyl isocyanate. This treated with OH minus. OH minus which mole? This is the first mole of OH minus. This is second mole. Here we have third mole. OH minus attack this particular carbon. C double bond of pi electron density moves away. You get R N double bond C COH CO minus. R N double bond COH CO minus. This is going to be obtained. R N double bond COH CO minus. And can I try to write the respective tautomerase structure here? R N double bond COH CO minus. If you try to write the tautomerase structure, what I can write, students? R NH C double bond O minus. This is the respective tautomer. Yes or no? R N double bond COH CO minus converting into R NH C double bond O minus. That will be the respective tautomer you are going to get whenever the third mole of OH minus attacked. R NH C double bond CO minus, that is now like negative charge on oxygen comes into, if you try to continue the reaction, R NH C double bond CO minus, negative charge on oxygen comes into, Cn electron density is given to nitrogen, leading to the formation of R NH minus plus a C double bond carbon dioxide. So this R NH minus will be picking up proton from the water. OH minus picks up the proton from the water, generating RNH2. And you have carbon dioxide, right? OH minus will be attacking the carbon dioxide, C double bond OH minus as soon as it attacks. Or instead of writing the reaction in this manner, you keep OH minus, the fourth mole of OH minus is attacking the carbon dioxide. OH minus, this is the fourth mole attacking the carbon dioxide, C double bond OH minus attacks the carbon, C double bond pi electron density moves away. You get a C double bond O minus OH. And we have RNH minus. RNH minus is reacting with the C double bond OH O minus. This RNH minus will pick up this proton. OH electron density will be given to oxygen, leading to the formation of RNH2. Along with RNH2, you generate C double bond O minus, which is nothing but CO3 2 minus ion. This CO3 2 minus will develop electrostatic force of attraction with Na plus ions. So this is nothing but Na2CO3. And what are the species lost in the previous steps? OH minus picked up the proton. So OH minus picked up the proton means H2O is obtained. In the first step also OH minus picked up the proton, H2O. So 2H2O obtained. Na2CO3 obtained, primary amine obtained. The bromide ion which is lost, in this stage as well as in this stage, they will develop electrostatic force of attraction with Na plus ions. So we have taken 4 NaOH, so we have 4 Na plus. 4 Na plus will be reacting. Out of 4 Na plus, 2 Na plus will be developing electrostatic force of attraction with CO3 2 minus. 2 more Na plus will be having electrostatic force of attraction with Na in a Br minus. Yes or no? Now the reaction, everything is satisfied, right? R C double bond NH2, Br2, 4 NaOH, RNH2, 1 mole of primary amine. Carbon the CO is removed as CO3 2 minus. Na2CO3 formed. 2 H2O and 2 NaBr are going to be formed. Primary amides converted to primary amines. Aliphatic and aromatic both are converted. 1 mole of halogen, 4 moles of base, and you will be getting 1 carbon atom less in the product because that carbon is lost in the form of CO3 2 minus. Is that clear? This was a complete mechanistic approach.
Yes, sir.
Yes, sir.
Yes.
Here we have seen the formation of R C double bond, like same mechanism, whatever the mechanism I have given, you follow that. Alkyl isocyanate, R N double bond C double bond O. Like methyl isocyanate, if you replace R with CH3, that the methyl isocyanate hydrolysis is directly written RNH2 plus CO2. That in the presence of 2 OH minus forms CO3 2 minus. But instead of this direct way, you follow our way. Like whatever discussion I have done with the mechanistic approach. Isocyanate treated with OH minus forms R N double bond COH CO minus tautomerized RNH C double bond O minus. Then the RNH minus obtained along with CO2. 4th mole of OH minus attacks CO2. HCO3 minus. That HCO3 minus will be picking up the proton from HCO3 minus will be picked up by RNH minus. So this is the total shift happening. Is that clear, students?
Yes, sir.
Yes. Yes.
Now I'll give a question to you. Try to answer this. What is the major product of that particular reaction? Very interesting question. Try to answer this. So mechanism you have studied, everything you know. But now I have introduced the concept of stereochemistry. So first what happens, the C double bond is going to be lost. If you look at the overall course of the reaction, this alkyl group is going to be shifting and attacking the nitrogen. Yes or no? In the process of mechanistic
Yes.
approach, what you have seen is the alkyl group has been shifted. Look at this. The alkyl group has been shifted. Intramolecular alkyl shift occurred. Intramolecular alkyl shift. The intramolecular alkyl shift occurred and the attack of nitrogen has been happened. But if you include the stereochemistry with this alkyl group, the stereochemistry is going to be changed or not changed. If it is changed, how it is changed, that point you need to understand. It has been observed in the mechanism that the configuration of the migrating group R is retained in this reaction. What happens, students? The configuration of the alkyl group, and write down that point, note the configuration means the spatial arrangement of groups. The configuration of migrating group, which is a migrating group, the alkyl group R. The configuration of migrating group is retained in this reaction, is retained in this reaction. That means what? That means this configuration is not going to be changed. So hydrogen, deuterium, methyl, they will be having same positions. So C hydrogen, C deuterium, C CH3, that will be as it is. So option A will be the right option. Got it now?
Yes, sir. Sir.
That's right. So next question, example. So what type of reagents you can take in this method? X2 in the presence of alkali medium means Br2NaOH, Br2KOH. Br2NaOH means you can take as NaOBr, NaOCl. Br2KOH means KOBr, KOCl. Like that also you can take. And NaOH is a milder oxidizing agent. We all know that. Yes or no? Instead of Br2 and NaOH, they can also mention NaOBr. Then also you have to, like whenever you see amide treated with NaOBr, you have to think of Hoffman's bromamide degradation. You have to think of Hoffman's bromamide degradation. Like you take this C double bond NH2 and here you place a deuterium and same C double bond NH2 and nitrogen here is going to be N14 isotope and here C double bond NH2 N15 isotope. If you do this, what are the correct sets? Set A is you are getting this compound N14 deuterium plus N15 NH2. Second set is deuterium N15 NH2 N14 NH2. Same NaOBr. I have taken mixture of amides now. Instead of taking just only one type of amide, I have taken mixture of amides. In one amide, I have C double bond NH2 where isotope N14 has been introduced. In the other amide, I have placed C15 isotope. Then I have treated with NaOBr. So we have seen the mechanistic approach that intramolecular alkyl shift occurred. That shift is intramolecular only, not intermolecular. Okay, you cannot shift this particular group and attack this particular nitrogen to generate C6H4D NH2. That is not possible. Since the shifting occurs, the shifting, okay, alkyl shifting is alkyl shift occurring in Hoffman bromamide degradation. Hoffman's bromamide degradation is intramolecular shift, intramolecular and not intermolecular. From the mechanistic approach also we have explained Italy, and that has been studied experimentally as well. So only intramolecular shift happens. So whatever this phenyl group is shifting, that will attack only this N14. So N14 NH2 will be having deuterium, and this shift whatever is happening, that will attack only N15 NH2, not the shifting. This phenyl cannot attack NH2 of N14, or this phenyl with deuterium cannot attack NH2 of N15. Understood this point or not?
Yes, sir.
Yes.
Okay, so only intramolecular shift is happening, not intermolecular shift. So that is how you have to shift. And the alkyl group, whatever it is shifting, that will retain its configuration. The configuration is not going to be changed. Right, students? Benzamide you treat with Br2 in the presence of NaOH, you will get aniline directly. Yes or no? Because the shifting happens. NH2, Br2 NaOH. Acetamide, you get primary amine, CH3NH2, methanamine you will get. Very simple questions. Benzoic acid treated with NH3 and heating. Benzoic acid you take C double bond OH treated with NH3. Ammonium benzoate is going to be formed. C double bond O minus NH4 plus. C double bond O minus NH4 plus upon heating, you will generate respective C double bond O NH2 respective benzamide you will get that treated with NaOBr. NaOBr means NaOH plus Br2, Hoffman's bromide degradation. So we generate respective aniline. This is the major product. Everyone got it or not?
Yes.
Yes, sir.
Yes, right.
Yes.
So that is how we can have different types of reactions. Example, benzoic acid with PCl3, PCl5, SOCl2. You are getting what? Nucleophilic substitution is going to happen. You get C double bond O. COH is going to be replaced by CCl. So this particular compound, like acyl halide substitutions that are treated with NH3, benzoyl halide treated with respective NH3, what is going to happen? The nucleophilic substitution occurs. C double bond of Cl, nucleophilic substitution by addition elimination type. Lone pair of electrons and nitrogen attack the carbon, C double bond of pi electron and C moves away. You will get amides, CO minus, nitrogen with have positive charge, 3 NH bonds and a carbon chlorine bond. Negative charge on oxygen comes into, chloride leaves. Loss of chloride occurs. You have a benzene ring connected with C double bond O, connected to nitrogen, positive charge, 3 NH bonds. The chloride which is lost, that will try to pick up the proton. NH electron density will be given. So you get C double bond O NH2. This is compound A, and this is your compound B. Compound B treated with Br2 NaOH. Hoffman's bromide degradation. You get respective aniline back. And intramolecular shift happened. All these points you can know. This is your compound C. A, B, C figured out. Right, students? These are the different methods of preparations of amines. In the Hoffman's bromide degradation, you can prepare primary aliphatic as well as aromatic amines. Primary aliphatic as well as aromatic amines. In the Gabriel Thallimide synthesis, you can prepare only primary aliphatic amines. Ammonolysis, if you can do, you can get a primary, secondary, tertiary, quaternary mixture. where you will be, if you take ammonia excess, you will have primary amine as major. If you take alkyl halide excess, you have quaternary ammonium salt as excess. And reduction reactions, you have seen reduction of nitriles, isonitriles, nitro compounds, as well as amides and oximes as well. So these are the different methods of preparations of respective amines. If you go with the next property, solubility. Lower aliphatic amines are soluble in water because they can form hydrogen bonds with water molecules. If you consider lower aliphatic amines, they are soluble because they are forming the hydrogen bonding. And if you increase the molecular mass, what happens? The alkyl chain length, if it is increased, like alkyl chain is a long chain, RCH2 taken 10, NH2 let us take. This is all hydrophobic. This hydrophobic chain length, if it is increased, whatever the water molecules we have near this hydrophobic chain, they are not going to develop new interactions. So with increase in molecular mass, that is with increase in the chain length, the solubility of respective amines is going to be decreasing. Whereas lower aliphatic amines are soluble in water. Lower aliphatic amines are soluble in water because they can form hydrogen bonds with water molecules. Solubility decreases with increase in molar mass of amines due to increase in size of hydrophobic alkyl part. Hydrophobic means new interaction with water not developed, water repelling, hydrophobic phobia. And higher amines are essentially insoluble in water. Obviously, if you increase the chain length further and further, the solubility is going to be decreasing. They are going to be insoluble in water. This is what about solubility. Solubility, whenever you are talking, you have to always think of intermolecular force of attraction developed with the solvent. Whatever the compound, organic compound you take, alkyl halides, aromatic compounds, carbonyls, carboxylic acid, whatever you take, solubility means new interaction developed with the solvent and solute. Boiling point means the interactions between two solute particles, intermolecular force of attractions. So boiling point, primary and secondary amines are engaged in intermolecular association due to hydrogen bonding between nitrogen of one and hydrogen of other molecule, because hydrogen bonding is there. But secondary, primary and secondary will have hydrogen bonding, but tertiary will not have hydrogen bonding. So primary will have how many hydrogen bonding sites? Primary RNH2. How many hydrogen bonding sites are there in primary? 2 NH bonds, 2 hydrogen bonding sites. Secondary RNHR, 1 hydrogen bonding site. RNR, R3N, 0 hydrogen bonding site. So if you try to compare primary, secondary and tertiary amine, primary amine will be having greater than secondary amine greater than tertiary amine. This is the order of boiling point based on hydrogen bondings, but this is true only when the primary, secondary and tertiary amines have same molar mass or similar molar mass. For similar molar mass. Understand this point carefully. You cannot take a primary amine like CH3NH2 and you cannot compare with the tertiary amine like CH3, NCH3, NCH3. If you are doing the comparison with CH3NH2 and CH3 taken thrice N, you are wrong. Because molecular mass has been changed or not. If you are comparing primary, secondary and tertiary amine, the primary, secondary and tertiary amine should be of similar molar mass. Like the primary amine here you have to take is CH3, CH2, CH2, CH2 and H2. How many CH are there? 3, right? So you have to take CH3, CH2, CH2 and H2. This primary amine you have to compare with this tertiary amine. You are not supposed to compare CH3 and H2 with CH3 taken thrice N because the molecular mass is going to be different. Got it? Primary and secondary amines are? Yes, right? Very good. Primary and secondary amines are engaged in intermolecular association due to hydrogen bonding between nitrogen of one and hydrogen of other. This intermolecular association is more in primary amine because 2 hydrogen bonding sites than in secondary. In secondary, we have only 1 hydrogen bonding site. Tertiary amines do not have intermolecular association due to absence of hydrogen atom required for hydrogen bond formation. So the order of boiling point will be primary greater than secondary greater than tertiary for what? Of same molecular mass. of same molecular mass, the primary will be greater than secondary, secondary greater than tertiary. That will be the order of boiling point. CH3, CH2, 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 NH2, that will be greater. Then you have C2H5, NH, C2H5. This is the primary, this is secondary, this is tertiary. Look at the number of carbons. 1, 2, 3, 4. 2 plus 2, again 4. 1, 2, 1, 2, 3, 4. Again 4. Like 4 carbons, 1 nitrogen. Hydrogens automatically going to be same. So with the same molecular mass, if you try to compare primary greater than secondary, secondary greater than tertiary, that is the right order of boiling point. Is that clear, students?
Yes.
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 Yes, right. Very good. Reaction showing basic nature. Amines being basic in nature react with acids to form salts. Like RNH2 react with HCl. Lone pair of electron present on nitrogen, they can be attacking H plus ion. RNH2 react with HCl. Amines, they are basic in nature. So lone pair of electron present on nitrogen, they will be attacking H plus to form what? New NH bond is going to be formed. RNH3 plus and Cl minus. The electrostatic force of attraction will be there. RNH3 plus Cl minus. C6H5NH2 plus HCl, that will form C6H5NH3 plus Cl minus. Amine salts on treatment with the base like NaOH regenerate the parent amine. Why? Because amines are basic in nature. So respective RNH3 plus Cl minus, they have a tendency to undergo loss of H plus ion. Because nitrogen has a positive charge, the NH electron density will be moving toward nitrogen. This NH bond is polar bond. So if you treat this with a base like NaOH, this base can easily pick up this proton, strong base, and it will regenerate back RNH2 and Cl minus, and base and proton will be there. RNH3 plus Cl minus reacting with a strong base like NaOH regenerates the primary amine and H2O, or instead of H2O you can write a base forms a new bond with hydrogen. Here base is NaOH we have taken. So OH minus picks up the proton. So OH and H is nothing but H2O. Cl minus is there in the reaction mixture. So this reaction of amines with the dilute acids, the reaction of amines with the acids also support the basic nature of amines. Amines are going to be basic in nature because they are going to be reacting with acids to form salts, and they are going to regenerate the parent amine whenever the respective salt has been treated with a strong base like NaOH. And what is the order of basic nature? Like among primary, secondary, and tertiary amine, in amines, what is the order of basic nature? In a gas phase, let us compare. If you try to compare the basic nature of amines in gas phase, tertiary amines are more basic than secondary, then primary, and least is going to be ammonia. Because in tertiary amine we have more alkyl groups. Because of the presence of more alkyl groups, electron density on nitrogen increase greatly, then secondary and then primary, and least is going to be ammonia. But if can we do the same reaction? Can we do the same reaction with respect to, like, can we compare the basic nature of amines in aqueous phase?
No,
In
No,
aqueous
sir.
phase, what happens?
secondary
Solvation occurs.
Yes or no? Solvation occurs. What are the different factors on which you can think of basic nature of amines, like in the aqueous phase?
Steric hindrance, hydrogen bonding.
Yeah, steric hindrance, hydration.
inductive effect.
Yes. So let us proceed that. In aqueous phase, the basic nature of amines is a result of the basic nature of amines is a result of hydration, electron donation tendency, and steric hindrance. Steric hindrance. So based on all these, based on combined effect, For methanamines, what is the order?
2 degree, 1 degree, 3 degree.
2 degree, 1 degree, 3 degree, and ammonia. For ethanamines,
2 degree.
2 degree, 3
Secondary,
degree, 1 degree.
tertiary,
secondary, tertiary, primary, and ammonia. Okay. So this is a combined effect of all the hydration. The same thing, if you remember, we have discussed in GOC. Yes or no?
yes, sir.
Yes, sir.
Okay. So for ethanamines, 2 degree, then 3 degree, then 1 degree, then ammonia. For methanamines, 2 degree, 1 degree, 3 degree ammonia. And whenever you are comparing some rings, whenever lone pair of electron nitrogen attack the H plus, if we are getting anti-aromatic compounds, that is going to be highly unstable. Because of that, that is going to be least basic in nature. Such compounds also we have discussed. And in aromatic amines, lone pair of electron present on nitrogen. So electron donating group will increase the electron donating group increases basic nature, and electron withdrawing group decreases basic nature. So based on the type of groups connected, you can compare which are going to be more basic and which are going to be less basic. When compared to aromatic and aliphatic are more basic when compared to aromatic, because in aromatic lone pair of electrons and nitrogen, they were in resonance. Because of resonance, the net electron density on nitrogen, that has been decreased. So when you try to compare aromatic and aliphatic are more basic when compared to aromatic. But if you are trying to compare among aromatic amines, then you have to think of what type of groups are present, electron donating group or electron withdrawing group. Based on the type of groups present, you have to decide which is going to be the right one or not. Is that clear?
Yes, sir.
Yes, sir.
Acylation. Aliphatic and aromatic primary and secondary amines react with acid chlorides, acid anhydrides, and esters by nucleophilic substitution reaction. Ethanamine react with a CH3 C double bond of Cl in the presence of base. Lone pair of electrons present. If you look at the mechanistic approach, like C2H5NH2, lone pair of electron present on nitrogen, they are reacting with acyl halides CH3 C double bond of Cl. As soon as the attack pi electron density moves away, you will generate what? C2H5 NH, 2 NH bonds as it is, nitrogen plus a positive charge. Nitrogen form a new bond with carbon, oxygen CO minus, CCH3, CCl. Negative charge and oxygen comes into chloride leaves, loss of chloride occurs, generating C2H5, 2 NH bonds, positive charge, C double bond of CH3, and you have chloride ion. The chloride ion easily picks up the proton. So NH electron density is given to nitrogen, generating C2H5, NH, C double bond of CH3. C2H5, NH, C double bond of CH3. So ethanamine react with the respective CH3, C double bond of Cl to form what? N-ethyl ethanamide. What is this? On the nitrogen, we have ethyl substitution. CH3, C double bond of NH2 means ethanamide. Yes or no? CH3, C double bond NH2 is amide, ethanamide, but N-alkyl. So N-ethyl ethanamide is obtained. CH3, C double bond, if we have NH2, it is said to be ethanamide. But we have NHC2H5, which is said to be N-ethyl ethanamide, and HCl is lost. The base pyridine has to be taken. The pyridine will be reacting with HCl. The pyridine will be the base pyridine. The base pyridine will be reacting with HCl, and the reaction moves in the forward direction. Is that clear or not?
Yes, sir.
Yes.
Okay. And the base, generally pyridine or pyridine derivatives we are going to take, which are stronger bases, not the weaker bases. The stronger base we have to take. Why? because HCl is a strong acid. The strong acid will be reacting with strong base. Okay, HCl is a strong acid. If you take a weak base than the respect to ethanamine, then obviously HCl will react with the respect to amine, not the base whatever you have taken. Okay, pyridine or derivatives of pyridine you have to take. So the strong base we have to take, not the weak base. The stronger base has to be taken. The base used in this reaction should be a stronger one, should be a stronger base than the amine, If not HCl will react with amine. HCl will react with amine. Yes or no? Amines will have acidic. Amines will have a tendency to react with acids to form the respective salts. The base used in this reaction should be a stronger base than amine. If not, the HCl will react with the amine, leading to the formation of salts, not a weaker base. So you can choose pyridine or derivatives of pyridine where the basic nature is greater. So that stronger base will be reacting with a strong acid. So HCl reaction with respect to amine is going to be restricted. If not restricted, HCl is a strong acid that will react with ethanamine, and it will not initiate the forward direction greatly, because HCl, as soon as it is formed, it will react with the ethanamine. So no amide formation, no acylation happening. Okay. So acylation reaction. After that, we have taken N-ethyl ethanamine also. N-ethyl ethanamine you can take with acyl halide, you can take, as well as acetic anhydride also you can take. Acetic anhydride also you can take, because acyl halide and acetic anhydride both are electrophilic in nature. They can be attacked by the lone pair of electron present on nitrogen easily. So N-ethyl ethanamine treated with CH3 C double bond to Cl. Lone pair of electrons, same type of reaction. They attack the carbon, C double bond to moves away. Loss of chloride picks up the proton. So you get C2H5, N C2H5, C double bond to CH3. If you don't have the C2H5 groups, if you have NH2, what is it called as? If you don't have the C2H5,
Acetamide.
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 yeah, ethanamide we can call in the IUPAC nomenclature, because 2 carbons are there. We can call it as acetamide also, or ethanamide. So on the N we have 2 alkyl groups. What are those? Ethyl groups. So N, N diethyl ethanamide, that is the respective name. N, N diethyl ethanamide, and HCl is obtained. So base has to be present, which is a stronger base. Will remove the HCl from the reaction mixture. N, N diethyl ethanamide is going to be formed. If you take aniline or benzamine, lone pair of electrons on nitrogen, they will attack the carbon, C double bond moves away. So here acetate ion is lost. The acetate ion will pick up the proton. You get what? Acetic acid. Along with that, you will get C6H5 group substituted with NH, C double bond to CH3. If we just have CH3, C double bond NH, what is it called as? If we have NH2 instead of C6H5, it is called as ethanamide. But on the N we have phenyl group, so we can call that as N-phenyl. N-phenyl ethanamide. That N-phenyl ethanamide can also be called as acetanilide. Acetanilide. Okay, remember these common names also. So whenever you do the acylation of respect to aniline, you will be getting N-phenyl ethanamide or acetanilide. Along with that, the leaving group is acetate ion. The acetate ion picks up the proton, so you will get acetic acid. C6H5 NH, C double bond to CH3, N-phenyl ethanamide or acetanilide. Along with that, acetic acid is obtained. Is that clear, students?
Yes, sir.
Yes,
Yes,
sir.
This is the acylation of respect to amines. And after the reaction of amines with acids and then acylation, we can go with Hoffman's carbolamine reaction or isocyanate test. Aliphatic and aromatic primary amines on heating with chloroform and ethanolic potassium hydroxide KOH from isocyanates or carbolamines which are foul smelling. This was a reaction. Primary amine react with CHCl3 and KOH upon heating form RNC. You can see this set in which other reaction? CHCl3 KOH. Raymond-Timon reaction. So what happens? What is the intermediate there? Raymond-Timon reaction.
Dichlorocarbene.
Dichlorocarbon, very good. So OH minus from the KOH picks up the proton. CH electron density given to carbon. Carbon chlorine leaves. You will generate water. Along with water, you will generate CCl2, and along with CCl2, you generate chloride ion. CCl2 is a strong electrophile or not?
Yes, sir.
It is a strong
Yes, sir.
electrophile because it has six electrons around itself. So now it has a electrophilic tendency. So primary amines RNH2 react with CCl2. Lone pair of electrons and nitrogen, they attack the carbon. Carbon already has one lone pair. Generate what? R. Nitrogen has two NH bonds. Positive charge. Positively charged nitrogen connected with carbon. Carbon has two carbon chlorine bonds and a negative charge on carbon. Negative charge should be present on carbon. Why? Because neutral atom gained the electron density. Now what happens? OH minus picks up the proton. So NH electron density is given to nitrogen. You will generate what? RNH. Nitrogen regains its lone pair. C minus CCl. Yes or no? C minus CCl. Now, if you try to proceed this, lone pair of electrons and nitrogen comes into, because chlorine is an electron withdrawing group. Carbon and chlorine leaves. Loss of chloride occurs. RNH. Nitrogen used this lone pair. So positive charge on nitrogen. Nitrogen positive charge. Carbon negative charge as it is. Chloride is lost. And you will have another Cl. Only one carbon chlorine bond is there. Whatever the chloride lost, that can pick up this proton. Cl minus can pick up this proton. And NHL, or we also have OH minus, right? OH minus base itself is there. So that base itself can pick up the proton. When compared to Cl minus, OH minus is obtained from the base, strong base that can pick up the proton. NH electron density given to nitrogen. So Rn, nitrogen regained the lone pair. N double bond C minus CCl. It will form what? Lone pair of electrons and nitrogen comes into carbon chlorine leaves. Loss of chloride ion. Generate R N triple bond C, carbon negative, nitrogen positive. This is nothing but an isocyanide. The chlorides lost will develop electrostatic force of attraction with the K plus ions. So along with that, you will generate KCl. OH minus picks up the proton, so you will get H2O. Everyone understood this or not? K plus KOH we have taken. So K plus ions will develop electrostatic force of attraction with Cl minus. We form KCl. And we have OH minus picking up the proton, so we form water. Isocyanide is going to be formed. Isocyanide is actually a foul smelling substance. So that is why it is also called as carboylamine reaction. And whenever you see a foul smell, that you have to understand they were talking about carboylamine reaction and all. They were talking about carboylamine reaction. You have to understand in that way. Is that clear? This was the mechanistic approach.
Yes, sir.
Yes, sir.
Yes, sir.
Right. Aniline treated with a CHCl3KOH, what happens? Same reaction. Here you will be generating CCl2. CCl2 will be attacked by lone pair of electrons and nitrogen. You will get a foul smelling substance like N triple bond C, carbon negative, nitrogen positive. So you can just say this as phenyl isocyanide. Phenyl isocyanide is going to be obtained whenever aniline reacted with a CHCl3 and KOH. CH3, CH2, NH2, CHCl3, KOH, carboylamine reaction. So CCl2 is the electrophile. You will get A, compound A is CH3,
CH3,
CH2, N triple bond C,
NC.
and LiLH4. Like isocyanates treated with lithium aluminum hydride forms CH3, CH2, NH, CH3. Secondary amines are obtained. Yes or no? Secondary amines are going to be obtained whenever you treat the respective isocyanates with the lithium aluminum hydride. We have discussed this reaction. Reduction of cyanates will give primary amines. Reduction of isocyanates will give secondary amines. And this was the mechanistic. This was the reaction, and the products are given to you in respective cases. Is everything clear, students, so far?
Yes, sir.
Yes,
Yes,
sir.
sir.
That's right. So we have next test also. So we can just go with the reaction of benzene sulfonyl chloride, Hinsberg reagent. It is used to distinguish between primary, secondary, and tertiary amines. We'll do it in the next class because the mechanism also we have to write a solubility with alkali. We have to explain all that. Okay. Thank you all, everyone. Bye.
Thank you.
Thank you, sir.
Thank you, sir. Thank you, sir.